Now, I said in the last presentation that where sets are concerned, it's their members that counts, and not the way in which they're written, the way in which they're described, or the number of times they're written, where we write out sets by enumerating their members within curly brackets. You shouldn't, however, read into that more than is intended, because when we write out some groups, the order clearly does matter, and we call such groups sequences. A sequence is an ordered group of objects, and we're all familiar with sequences in everyday life. In elementary mathematics, for example, in simple algebra, we'll know that on the Cartesian plane, the point 1, 2, that's 1, x value of 1, y value of 2, is not the same point as the point with an x value of 2 and a y value of 1. And by the same token, while we say that order doesn't matter when it comes to writing out sets, so the set comprising the two positive integers 1 and 2 is the same as the set which comprises those two integers, even though they're written in reverse order, still the set containing the one object, which is the ordered pair of 2 and 1, and that ordered pair and the fact that it's a pair is signified by its inclusion in these parentheses, is not the same set as the set containing the one element, which is to say the ordered pair 1, 2. These are sets containing two elements, and moreover the same two elements, and so they are, by the axiom of extensionality, the same set. These two sets on the either side of this inequality sign are singletons. They contain one object in each case. That object is an ordered pair. In the first case, it is the ordered pair 2 and 1, and in the second case, it's the ordered pair of 1 and 2, and those are not the same thing. Now we're going to turn to the notion of relations, and of course we're familiar with them in all sorts of everyday contexts. We relate people to people, describing them as siblings, for example, or whatever. We relate numbers to numbers, as in the case of being equal to one being equal to another, or greater than another, and so on and so forth. A relation is something which binds a number of objects. In the case of the greater than relationship among natural numbers, that will be two objects. In the case of the located at relation in three-dimensional space, for example, three objects may be involved: an x-axis dimension, a y-axis dimension, and a z-axis dimension. More generally, a relation involving n objects, as a matter of terminology, is said to be an n-place relation or an n-ary relation. So the wife of relation, for example, is a two-place, or we sometimes describe a two-place relation as a binary relation. The between relation is a three-place relation. It's something is between two other things. A three-place relation, sometimes termed a ternary relation. Another piece of terminology here, a one-place relation, because relations, there's no need to limit this n to numbers greater than 1. A one-place relation is said to be a unary relation. Now, unary relations are things that we are more familiar with in everyday life as properties. Now, most relations define sets. I say most relations define sets because, for example, having the identity relation define sets can lead to some of the set theoretic paradoxes with which some of you may be familiar with, but which lie well beyond the scope of this course. The wife of relation, for example, is the set of all married couples. So the wife of relation defines a set in which appear pairs, as signified here by these parentheses, and the pairs are in the first case the wife, and in the second case the person of whom she is the wife. So Mary and John, then the pair Alice and Ralph, and so on, including all married couples. Now that is not the same set as the set again containing ordered pairs. The pairs, the fact that each element is a pair, is signified by the inclusion of these parentheses here, where the first member of the ordered pair is in fact the name of the husband, because John is not the wife of Mary, Ralph is not the wife of Alice, and so on and so forth. Now the set of things which appear in the n-tuples which make up an n-ary relation, an n-tuple is simply a group with cardinality n, that is to say a group of n things. The set of things which appear in the n-tuples which make up an n-ary relation is termed the domain of the relation. So the domain of the white relation which is a unary relation, so the n-tuple is a one-tuple, it's just single things. The domain of that relation, the white relation, is the set of all white objects. The domain of the wife of relation is the set of all married people, pairs of which are in the relation. Now let's turn to functions. As with relations, we're all familiar with functions in everyday life, and when we use expressions such as depends upon, for example, we will often be invoking some sort of function. Functions correlate objects with objects. The birthday function, for example, correlates each person with a date, which is more specifically the date of his or her birth. More generally, a function, f, correlates an object, x, with another object, f of x. Sometimes we say that f takes x to fx. You'll note here that fx is simply an object. Sometimes we'll say alternatively that f maps x to the object fx. Now, if fx is a function of x, then the set of things from which x takes values is termed the domain of f. The set of things from which fx takes values is termed the range of f. And so, by what I said a moment ago, a function f will take an object in the case where the function has, we say, one argument. It will take a single object from its domain to an object in its range. The domain of the birthday function is the set of all things, which is to say people, which have birthdays, given that we don't normally talk about animals having birthdays. And the range of the birthday function is the set of all dates on which those things, those people, were born. Now for some definitions. We say that a set X is denumerable if it is equinumerous with the natural numbers. That is to say, if its cardinality, which is the number of elements contained within it, is equal to the number of natural numbers. Now, of course, the number of natural numbers is infinite. We say that a set X is finite if it can be completely counted off, if its members, we can count its members, we can count off its members from 1 to some natural number n. And we say that a set X is countable if its members, again, can be counted off, whether or not the counting off process would have an end. Now, given these definitions of a countable set and a finite set, we see that a denumerable set which is one which is equinumerous with the natural numbers, has the same cardinality as the set of natural numbers, is not finite, but it is countable, even though counting off its members would be a process without end. Now that's going to finish the presentations on set theory. I've set out these concepts and this terminology and notation related to set theory because we will use it when we come to the semantics associated with logic. Now, in the written presentations, in the written papers available via the website, there are some exercises for you to go through, and there are some additional details. But in these videos, I've covered the bare minimum that we will need in order to understand the set theoretic semantics as they're described later in this course.